Hi, I'm John Aynsley from Doulos. Welcome to today's webinar, UVM Runtime Phasing, the full picture. So during this webinar, for the first time I'm going to be explaining in great detail the runtime phasing mechanism of UVM. Let's see what it's all about. Why should you be interested in the runtime phasing mechanism at all? Well, suppose you've got some verification IP. That verification IP does something. So here it might be resetting its part of the DUT, configuring part of the DUT, and so on. And we then want to integrate it with other verification IP that's also running a series of sequences, resetting, configuring, training, and so on. Well, the main point about the runtime phasing mechanism is that it provides a way of synchronizing the activity of stimulus across multiple bits of verification IP that you're throwing together. So we take the verification IP on the left, verification IP on the right, crunch them together, and we can then use the runtime phasing mechanism to synchronize all of that activity. It may be that we want to carefully order the activity of these two bits of verification IP. So here the reset activity on the right has to occur before the reset activity on the left, and we can accomplish that using runtime phases. So that's where runtime phases might be useful to you and why you might like to care about them. Just a little bit of background. OVM had phases, but only the build, connect, run phase and so on, not the runtime phases. Runtime phases, that is phases where simulation time passes, first got introduced with UVM. So UVM introduced runtime phases like the reset phase, the configure phase, and UVM also introduced phase synchronization and phase domains, user-defined phases, and also phase jumping, that's the ability to jump forward and backward along the simulation timeline. But we could regard all of these features as being kind of experimental in UVM 1.0. A number of UVM experts used to recommend that either you didn't use runtime phases at all, or you only used them very, very carefully when you considered yourself an expert in those runtime phases. In fact, for years at Doulos on our training classes, we've advised people to steer clear of runtime phases unless they knew exactly what they were doing. But in the latest version of UVM, UVM 1.2, runtime phases have been considerably improved. So I'm going to start off by looking at the concepts and jargon of runtime phases. Then I'll take a deep dive into a number of specific aspects of runtime phases, really to help you understand what they're all about, and also to explain a lot of the pitfalls. Some of this will be quite high level and will help you to understand the main concepts. Some of it will dive into the nitty-gritty detail, but really only where there are things I feel I need to point out to avoid you making mistakes. Toward the end of the webinar, I'm going to be focusing on VIP integration, which is the main objective of all of this stuff, as I've said, and also make a number of specific recommendations of do's and don'ts. So here goes. When we start to talk about phases in UVM, we've got to deal with a fair amount of nasty jargon. And the first bit of jargon we're going to meet is the idea of the common phases in UVM. So common phases is a very specific bit of technical jargon with a specific meaning. These are the common phases in UVM. You'll recognise them. Build phase, connect phase, run phase, extract phase, and so on. So those are the common phases. Remember that term. Associated with each phase, we've got three things: a class, and a method, and an object. And that can be a bit confusing when you first see it. So build phase is actually a phase method, and that phase method is associated with the UVM build phase, which is actually a class. So somewhere in the UVM base class library, there's a class UVM build phase that represents the build phase, and then you override the build phase method in your components in order to say what happens in the build phase. Then the build phase method is called with an argument, and that argument is a reference to a so-called proxy object, and that proxy object is the thing that represents the build phase at runtime. So the UVM build phase class is the build phase if you like, but classes only exist at compile time, and the proxy for that at runtime is this phase object that's referred to from the argument from the build phase method. So inside the build phase method, we could actually check this phase. So here we're asserting that the phase is indeed UVM build phase. That's just illustrating the API. Exactly the same thing happens in the run phase. So when the run phase task is called, it's being called from the UVM run phase class, and we're passing in here a reference to an object that represents the run phase. And in fact, as you may be aware, the point of passing a reference to the phase object into the phase class is so that we can raise and drop objections associated with that phase. So in UVM, objections are very closely linked to runtime phases. Each runtime phase ends when the objection count drops to 0. So now for the UVM runtime phases. So UVM runtime phases is another bit of jargon. The term the UVM runtime phases refers to these specific 12+1 phases that you can see on the slide here. So run phase is a runtime phase. So are reset, configure, main and shutdown. So reset, configure, main and shutdown were 4 new runtime phases that got introduced with UVM. And associated with reset, configure, main and shutdown, there's also a pre and a post phase, which makes a total of 12 UVM runtime phases along this timeline that run in parallel with the run phase itself being a carryover from OVM. So the idea of these runtime phases is to use them for stimulus generation and only for stimulus generation. All UVM experts seem to agree on that. There's quite a few things about runtime phases that the experts disagree on, but one thing that they agree on is that they should only be used for stimulus generation. So the reset phase you would use for resetting the DUT, the configure phase for doing configuration or setup or training before the main work of the test, which is done in the main phase, and then the shutdown phase is used for orderly shutdown at the end of the simulation. So I've introduced 2 new bits of jargon now. The common phases, which are these guys here, and the UVM runtime phases, which are this bunch of predefined phases, all of which run concurrently with the run phase. And all of these phases are used for stimulus generation. So now let's take a look at phase synchronization. So what we can do within one of our components is to write one or more of the new UVM runtime phases. So here in this component that extends UVM env, we've got the reset phase, the configure phase, the main phase and the shutdown phase. So we've overridden each of these 4 phase methods. Then in a test we're instantiating 2 envs. So we're instantiating this env class twice to create 2 component instances, env1 and env2, and we've created those using factory methods in the build phase. So we've just got a hierarchy with 2 instances of this env class. And then, just because we can, in the test, we've also overridden the run phase method. This is just to show that you can actually mix and match the old run phase carried over from OVM with the new style UVM runtime phases. So let's see what happens in pictures. What's going to happen now is that the 4 runtime phase methods, reset, configure, main and shutdown, get synchronized across our 2 envs. So the reset phases start and end together, configure starts and ends together, main and shutdown all start and end together. And they're also synchronized with the run phase task. So flipping back a slide now, we can see that in the 2 instances of our env, env1 and env2, both the reset phases start together and they start at the same time as the run phase in the test. So you might be sensing a snag here when it comes to what it means for all these phases to end at the same time. How do you know that the run phase method will actually end at the same time as the shutdown phase? Well, you don't quite. Let's take a close look at it. Suppose we've got a couple of runtime phase methods that are synchronized with one another. Well, what this means is that both methods are called in the same time step. So this main phase task and this main phase task will be called in exactly the same simulation time step, and then they just do whatever they do. So this one might raise an objection and do a whole load of stuff, start some sequences, and this one similarly. Because of that, the two methods could very well return at different times. So this task might end at 500 nanoseconds, this one might end at 500 milliseconds, for example. You can't say a priori at what point in time these tasks are going to return, but what you do know is that the phase only ends when all the objections have been dropped. So that's the basic idea of phase synchronization. Now let's have a look at domains. It turns out domains are really useful when it comes to integrating verification IP and synchronizing stimulus across verification IP. So domains are really one of the keys that's going to make all of this stuff work for us. The basic syntax of phase domains starts off looking really simple. We can declare a variable of type UVM domain. So here in the build phase method of some component, the test in this case, we've declared ourselves a domain variable. We're then instantiating a couple of lower level components and instantiating the domain. So domain 1 equals new domain 1 is creating a new domain object and setting a reference to that object into the domain variable. We can then set one or more of our UVM components into that domain. So here we're calling menv1.setDomain domain1, and that's saying that env1 now belongs to domain 1. So env1 is now in domain 1, env2 isn't. What does that mean? Well, env2 goes into the default domain, and I'll show you what that's about over the coming slides. Let's look at this diagrammatically. So now our component env1, which is in domain 1, has our 4 phases: reset followed by configure followed by main followed by shutdown. Our components that weren't in domain 1 also have reset, configure, main and shutdown, and they're placed in the so-called UVM domain. Another piece of jargon, so another jargon alert coming up. The UVM domain contains the so-called UVM Run-Time Phases. So these guys are the UVM Run-Time Phases. Well, you might be glancing up at the top of the screen here and saying these guys are the UVM Run-Time Phases as well. Well, yeah, they kind of are, and I'll show you how that works in a minute. So the UVM domain, which is the default domain, contains all of the UVM runtime phases, and we've now got a new user-defined domain that effectively contains its own copy of the UVM runtime phases. But you can see that the two domains are not synchronized. So the basic fact about domains in UVM is if you've got independent domains, then the runtime phases are not, by default, synchronized across those two independent domains. But we can choose to bring them into sync. And that's the real sweet spot of all of this stuff. We've got explicit control over how we choose to synchronize or not the phases across these domains. So let's look at another example. Here, to keep things symmetrical, we've got two separate domains, domain 1 and domain 2, two instances of a component, env1 and env2, and we've chosen to place env1 into domain 1 and env2 into domain 2. What we can now do is choose to synchronize phases across domains. So we could make a call domain1.sync domain 2, and that would pull all the runtime phases in domain 2 into sync with all of the runtime phases in domain 1. So now we'd be back where we started. All of the UVM runtime phases are running in sync with one another. Or we could unsync them. So unsync actually unsyncs all of the phases across two domains. So the effect of these two lines is to do nothing whatsoever. It puts us back where we were to start with. So these are for illustration only, but they do just illustrate that it's very straightforward to synchronize or unsynchronize all the phases across two independent domains. More meaningfully, we could synchronize specific phases across our domains. So here we're saying domain 1 .sync domain 2 UVM main phase. So this line is synchronizing just the main phase across domain 1 and domain 2, leaving all the other runtime phases unsynchronized. Or we can synchronize different phases across the two domains. So here we're synchronizing the reset phase with the configure phase, which obviously begs the question, well, which reset phase and which configure phase? Is it the reset phase of domain 1 or the reset phase of domain 2? That kept me scratching my head a little bit when I first saw it. Well, the answer is it's simply done by order. So this means the reset phase of domain 1, because this is named first, is synchronized with the configure phase of domain 2. Diagrammatically, looks like this. So if you remember, we synchronized the main phases across both domains. So the main phases of both domains both start together and end together. And then we synchronized the reset phase of domain 1 with the configure phase of domain 2. So now, if we were integrating some verification IP, we could place the components of that verification IP in separate domains, and it's very straightforward to pick out parts of the stimulus in the domains and synchronize it with the equivalent stimulus in the other domain. Now let's take a look at user-defined phases. We're going to do a bit of a deep dive into user-defined phases, but I'm going to excuse that because it's helpful in reinforcing some of the concepts that we've learnt so far. If you're going to do anything with phases, then it really helps to have a very clear idea of the distinction between classes, objects, and methods, and we'll see that very explicitly as we look at user-defined phases. So there's 4 steps I'm going to go through in describing user-defined phases. Step 1 is to define a base class that first declares the phase method. So here we've got a user-defined class extended component that extends UVM component, and in that component we're declaring an empty virtual task, and the name of that task represents the type of our new user-defined phase method. So you'll see training phase a lot. Training phase is a totally arbitrary name that we just invented. That's the name that we're going to use for our user-defined phase. You can define as many user-defined phases as you please, in the same place or in different places, and you can combine different user-defined phases defined in different places with each other or with the predefined phases. So having defined the virtual function in the base class, we can then go on with the serious business of defining the class that's going to represent our phase. So here we're looking at the phase class. And when you define a phase class, that has to do 2 things. And I'm sketching them here in outline. And on the next slide, I'm going to fill in all the details, and it's going to look like a bit of an eye chart, just to give you a warning of what's coming. The skeleton here is that in a user-defined phase class, there's 2 methods that we have to define. A get method, and that get method is going to return the proxy object that represents that phase at runtime. So again, the point here is that my training class, although it represents our phase, because it's a data type, it's visible to the compiler, but it's not explicitly visible as something we can manipulate at runtime. If we want something we can manipulate at runtime, we need an object, and that object of type myTrainingPhase is going to be returned by this get function. Then the second thing that we need in any user-defined phase class is a task, and the job of this task is going to be to call our user-defined phase method. So exec task is going to call the training phase method that we declared as a virtual method on the previous slide. Okay, so having described the overall skeleton, now I'm going to fill in the detail. Here we go. A lot of code, I know. So at the top, we've just got some boilerplate code for the constructor. No big deal here. Then we've got the code that returns our proxy object. So for that, we've declared a local variable mSingletonInst, and that variable is just a reference to the object that's going to represent the phase. And the very first time we call the get function checks to see if this variable has been set yet. First time get is called mSingletonInst will be equal to null, so we'll instantiate a new object of this current class and set the reference into mSingletonInst and return that reference. Then on the second and subsequent times get is called, mSingletonInst will not be null, so we'll just return its value. So now exec task. Exec task is the task that's built into the UVM base class library. So here we're overriding a method that's defined in UVM task phase. And when we override that method, we have it call our user-defined phase method. So training phase is a method of the base class on the previous slide, my training phase. So when we call the training phase method, the variable we call it on has to have the type extended component. So here we're declaring a variable of type extended component and then simply executing a dynamic cast. So that dynamic cast is taking the object that was passed into exec task and trying to cast it to be an object of type extended component. And assuming that dynamic cast succeeds, we're then calling the user-defined phase method. So hopefully you can see what's going to happen. When the UVM engine runs, when all of our code is up and running and UVM transitions into the training phase, it's then going to call exec task, and exec task is going to call the training phase method for our particular component. So that's step 2. The next thing we're going to have to do is to make sure that the training phase is indeed called at some stage. At the moment we've defined a new phase, but we haven't actually specified when that phase is called. So to do that, we're going to have to hook this new user-defined phase into a phase schedule. So here we go. In some build phase method, which is going to be the build phase method of an env that's used to integrate verification IP or even a test, we're declaring a variable of type UVM phase to represent our schedule. We're then getting a reference to a schedule, and the schedule we're getting a reference to is being returned from get UVM schedule. So get UVM schedule is a method built into UVM. It's actually a static method of the class UVM domain, and what this method returns is the predefined schedule of the UVM domain. So can you remember what the UVM domain is? The UVM domain is the default domain. The UVM domain is simply the domain you're using by default if you don't do anything special with UVM runtime phases. So this is the one that comes for free. So as a result of executing this code, our schedule variable now contains a reference to an object that represents the schedule of the built-in UVM domain. And now we're simply adding our user-defined phase to that schedule. So we're calling schedule.add myTrainingPhase : get. And of course myTrainingPhase : get is simply the static method that we defined on the previous slide. So we're inserting the object that represents our phase into the schedule, and the remainder of the arguments say where we insert it. So we're inserting it after the configure phase and before the main phase. So our training phase is now going to be called between the configure phase and the main phase of the UVM schedule. Then step 4 is to override the training phase task to do precisely what we want it to do. So we can now extend our extended component and override the training phase task just as we would override any other phase task. So once you've created a user-defined phase, it behaves in almost every respect like a built-in phase. It's a task in this case, it's a task phase, it can consume time, it has objections, it ends when the objection count drops to 0. So now, what does our schedule look like? So here we see a graph, a diagram of the UVM domain, the built-in domain. So here we have the original UVM runtime phases, or some of them. We've only shown a couple of the pre and post phases. And here we've inserted the training phase into this graph, after the configure phase and before the main phase. So that means that training is synchronized with the beginning of post configure and with the end of pre-main. So here significantly, we've inserted a user-defined phase into the predefined schedule. So all components in the UVM domain, that's all components by default, are now going to see this training phase inserted. So now let's take a look at schedules. Let's start this section by taking a look at this add method of the schedule. So when we call schedule.add, we can insert a new phase into an existing schedule, and this add method has three arguments: before phase, after phase, and with phase, that we can use to determine how the new phase is inserted into the existing schedule. So here's our existing schedule with three phases: A phase, B phase, and C phase, and now we're saying add D phase. In this case, adding the D phase after phase A phase. So we're inserting our new D phase after the A phase, and this is what we got. So here's the A phase followed immediately by the D phase, and that means before B and C. So you can see the resulting transition graph here. D is executed before B and C. Had we chosen before phase, we'd have got a different result. So now we're adding the D phase before the B phase. So here's our B phase, and D is being inserted before the B phase, but inserted in parallel now with the C phase. So the beginning of the D phase will be synchronized with the beginning of the C phase. The end of the D phase is totally unsynchronized with respect to C, but it does immediately precede the B phase. And notice that what we're doing here is inserting phases into a schedule. This is not the same thing as synchronizing phases between schedules. So we've looked at after and before. There's a third argument we can use, that's with phase. So in this case, we're adding the D phase with the A phase. So what with phase means is that the new phase we're inserting is synchronized with the start and the end of an existing phase. So A phase and D phase will now start together. Then A and D both have to finish before we move on to B and C. So we've got this join here within our phase graph. A and D both have to complete. In other words, the objection count of A and D both have to drop to 0 before the B and C phases are started. Okay, now let's put some of that into action as we create more schedules. So what we're going to do now is create a schedule from scratch. And I feel I want to apologise that there's so much text on this slide, but the reason for all this text is that you're going to need all of this stuff if you actually want to get all of this working for yourself. So let's see what we've got here. We've got a build phase function, and that build phase function is defining a bunch of variables, and then we're creating some phases and domains and schedules. So the first thing we're doing is creating a brand new schedule by saying schedule equals new UVM shed UVM passive schedule. So here we're using new to create a new object. The variable is schedule. The schedule variable is of type UVM phase. So a schedule is just a fancy phase. And when you create a phase and want it to be used as a schedule, you signal that this phase is to be used as a schedule by passing in the second argument to the constructor UVM phase schedule. And note the name here, UVM shed. That's important important because it turns out that UVM shed name is actually built in. I also kind of like the idea of a UVM shed. You got a UVM shed in your garden? There you go. Anyway, next thing we're going to do is to add the predefined run phases to this schedule. And we're doing that with the static method UVM domain add UVM phases. So what that does is to populate the schedule with all of the predefined runtime phases. Those are the 12 phases starting with pre-reset and ending with post-shutdown. So this line of code is creating a brand new empty schedule. The next line is populating that schedule with all of the predefined runtime phases. And this highlighted line is totally optional. You don't have to do it. We could start an empty schedule and then start populating with phases one by one. So we've got our 12 phases, and now we're inserting our user-defined phase exactly as we saw previously. Here we're not inserting the user-defined phases into the UVM domain. In fact, at the moment, we're inserting this phase into a schedule that's not associated with any domain. So this is a brand new schedule, and we've inserted our user-defined phase into this brand new schedule graph we've created from scratch. And then, only then, do we add this schedule to a domain. So then we're instantiating a new domain object, which will initially be an empty domain with no schedule associated with it. Then we're calling domain1.addSchedule, and that adds our brand new schedule to this empty domain. Now domain1 actually has a schedule associated with it. Although domain 1 has a schedule associated with it, it turns out that if we go ahead and run our simulation at this point, this new domain isn't actually going to do anything. It's not going to do anything because it hasn't been associated with the common domain. Do you remember the common domain? What we have to do is to associate our new domain with the run phase of the common domain. That's what these two lines are doing. So the built-in static method getCommonDomain is returning a reference to the common domain, and then we're calling common.add to add our new domain into the common domain, synchronizing it with the UVM run phase. So now everything's going to happen as we might expect. Pre-reset phase of our new schedule gets synchronized with the start of the UVM run phase, and the end of the post-shutdown phase of our new schedule is synchronized with the end of the run phase. Then finally, we're calling menv1.setDomain, domain1, so that sets the domain of a specific UVM environment to use our new domain. There we go. So I know that was all a bit of a long story, but that's showing you in nitty-gritty detail some of the distinctions between phases and schedules and domains. So it turns out that schedules are fancy phases, where a schedule can contain multiple nodes organised into a graph. And a domain is then a very fancy schedule that's special in the sense that you can associate components with a domain and then synchronise domains with one another. Now we're going to take a deep dive into setDomain. And again, I kind of feel I want to apologise for this, but I'm not going to apologise for it. And perhaps I just did. Anyway, I'm not going to apologise for it because you really need to know it if you're going to use this stuff. There's some nasty pitfalls waiting for you in the behaviour of setDomain. To be honest, it's quite weird. Let's see what happens in detail. So here in the build phase method, in this build phase method, we're saying domain1 equals new domain1. What that does is to create a pristine new empty domain. Then we're calling menv1.setDomain, domain1. And what that does is to put the menv1 component into the domain1, and it also magically populates domain1 with all of the UVM runtime phases. What? How did that happen? It didn't happen on the previous slide. So if I go back to the previous slide, this call menv1 setDomain domain1 just simply sets the component menv1 to be in domain1, where domain1 is a user-defined domain that we've just created. Now it does a lot more than that. It not only puts mn1 into domain 1, but it also, on this line of code, populates domain 1 with all of the UVM runtime phases. That's quite weird. Let's see how it works. So setDomain is a method of UVM component. If we look into the UVM source code, we'll find that the definition of UVM component setDomain looks like this. So the first thing it does is to set the mDomain data member of UVM component. That's a perfectly reasonable thing to do. It puts our component into the domain. Then it calls the define domain method of that component. That's the one that does the dirty work. And then it recursively calls setDomain for all the children of the component. And in fact, you can program whether this works hierarchically or just works on the current component, but I won't show that here. So define domain is the thing we've got to worry about. The define domain method of UVM component looks something like this. This is just pseudocode, but it says what happens. So what the built-in define domain method does is it asks a question. It asks if there's any schedule that's called UVM shed in this domain. So if our domain already has a UVM shed, define domain does nothing. But if there's no schedule named UVM shed, then what define domain does is that it adds all of the predefined runtime phases to our domain. And then furthermore, it adds the domain into the common domain. In other words, it synchronizes our domain with the run phase method of the common domain. By default, if you just call setDomain, setDomain calls define domain says, there's no shed in this domain, so it adds all the predefined runtime phases and then it synchronizes that domain with the common domain. If you don't like it, you can do something else. So what you can do is to override the define domain method of UVM component to do whatever you want it to do. So here's an example. Here we've got our own user-defined environment, which extends extended component. We're overriding the virtual task training phase. We're defining our own training phase. And then, without creating our own schedule or domain, we're using the define domain method to add the training phase into our schedule. So overriding define domain is a two-edged sword. On the one hand, it's very flexible because it allows you to insert user-defined phases into the schedules of domains without going to all the fuss and bother of defining new schedules from scratch. So remember that long slide a few slides back that created a brand new schedule and a brand new domain? We can bypass all of that stuff and simply override define domain in order to insert the training phase into the schedule of the current component. That's one side of the coin. The other side of the coin is this thing is horrible and is just bristling with pitfalls. So that's a bit of a mixed metaphor. It has lots of pitfalls for you to fall into. So here we're overriding define domain. We're choosing to call super.define domain. So super.define domain is calling the built-in define domain method that we saw on the previous slide. So that's populating our domain with all of the UVM runtime phases. And then we're choosing to add the training phase in the right place in those runtime phases. So now we've actually seen three ways to insert a user-defined phase into an existing phase schedule. The first method we saw way back was to insert our user-defined phase into the UVM domain. The second method was to create a new schedule from scratch and insert the training phase into that new schedule. The third and final way is to override define domain to do it, which is less code than defining a new schedule from scratch if you can get your head around it. So if you override define domain, as we're doing here, you have the choice whether or not to call the define domain method of the UVM component class, whether or not to call the base class method. Here we're choosing to call the base class method to populate our domain with the UVM runtime phases. If you don't, you can add phases one by one from scratch. The second thing that we've got to be really careful about, the second pitfall, is when you call define domain, it in general is going to be inserting brand new phases into a schedule. If you add multiple components to the same domain, each of those components is going to have their setDomain method called. setDomain will call defineDomain, and if each defineDomain method just goes ahead and inserts extra phases into the schedule, that schedule will simply keep growing. So each time we call this method, we'll find another training phase added between configure and main phase, and another, and another. Wow, what a pitfall. So you insert a phase in defineDomain, call setDomain repeatedly, and the schedule keeps growing, which is probably not what you meant. So if you only want to add it once, you've got to catch it, and that's what this line here is doing. So it turns out this is the way that you can make sure that defineDomain only does its thing once. You do it by checking whether the parent of the domain is null. To show an example of this in action, here we are in the build phase method creating a brand new domain, so you know now that this will be a pristine empty domain with no schedule associated with it. Then we're calling component instance.setDomain domain1. So assuming that this is using the code on the previous slide, it's going to populate our domain with all the predefined phases and the training phase. Then we're calling setDomain again for mnv setDomain. So all this does now is to add mnv to domain 1, but it doesn't add an extra bunch of phases because of that test we saw on the previous slide. Then we're instantiating a brand new domain, and we're adding yet another component to domain 2, and that's going to call defineDomain for domain 2 and populate domain 2 with the predefined phases and the training phase. Okay, now let's take a look at the topic of phase awareness before we finally look at VIP integration. UVM actually gives you three callbacks, three methods of a UVM component that you can use to check out what happens when you start and end phases. They are phase started, phase ready to end, and phase ended, and they get called pretty much when you would expect them to be called. So phase started is called at the start of a phase. And I really don't think this method has any obvious purpose, except maybe for debug. So phase started is called when any phase is started for a component. So here we're overriding phase started to simply print out a message to show when each phase has started. The one thing to notice about the start of any phase is that you've got to raise an objection before the first NBA region of that phase. If you don't raise an objection before the first non-blocking assignment region, then the phase will end in the very same time step in which it started. So phase ready to end is called when the phase is ready to end but not necessarily ended. That is, it's called when the objection count drops to 0. So phase ready to end I like to think of as last chance saloon for a phase. So phase ready to end gives a component a last chance to stop the phase ending and actually extend the phase. So phase ready to end actually gives you a chance to raise objections and thus extend the phase. So what we're doing here in this particular overriding of phase ready to end is to check which phase we're in. So this if test says if we're in the main phase, then if it's the first time we've been through this bit of code, then we're raising an objection. Waiting for some time, and then dropping the objection. So by doing this, we've extended the phase. The phase has pretty much come to an end, and you say, no, I want to continue it a little bit longer by raising another objection. And you only get 20 shots at that. So there's actually a fixed magic number of 20 in the UVM base class library, and this loop would only work 20 times. It would crash out after you'd attempted to extend the phase 20 times per phase. Well, I'm telling you this really just so that you know that the mechanism exists. I know certain UVM experts recommend that you use phase ready to end as a way of extending the phase. Frankly, our view at Doulos is that this is sticking plaster or band-aid. It's really not terribly good practice. The problem with this practice is, in our opinion, it's actually an abuse of objections. The idea of objections is that deciding when a test is over is actually intrinsically a distributed process. It's not a process you can execute procedurally. It's a process that all of your components need to take responsibility for. So the right way to deal with objections is to raise an objection when you're busy doing something and to drop the objection when you really are ready for the test to end or for the phase to end. Implicitly, this code suggests that the component has dropped the objection before it was ready, because here we are raising the objection again. Nonetheless, it is a mechanism in UVM that is available for use, but beware, this method is not called if the phase ends prematurely. So if you jump out of a phase before the phase comes to a natural conclusion, then phase ready to end doesn't get called. Whereas phase ended does. So phase ended is called once, however the phase ends. So if you go kill the phase, kill the processes in the phase, jump out of the phase, whatever you do, phase ended is always called once at the end of the phase, and you don't get any second chances. So here, just to prove the point, we're checking that the phase variable, the objection associated with the phase variable is set, which it will be, and then we're asserting that the objection count is 0, again, that it will be. So phase ended is only reached when the objection count is indeed 0. So these highlighted lines are just really for illustration of what's going on. What we can then do is to say, well, if our component is still busy, tidy it up. mBusy isn't a built-in variable, it's just a user-defined flag we've set to show that we've got some tidying up to do. So we can use phase ended for housekeeping code to tidy up at the end of our phase. And that segues nicely into the general idea of making components and sequences phase aware and why you'd want to do that. So making sequences and components phase aware is always something that you should only do as a last resort because it's going to make the code harder to maintain. You can make sequences phase aware by making use of the starting phase variable, and as you may know, in UVM 1.2 you get access to the phase in which a sequence is running by calling getStartingPhase. That replaces the starting phase variable from earlier versions of UVM. And what we can now do is to say, if starting phase is set, call phase.waitForState. This is the equivalent for phase ready to end when you happen to be in a sequence rather than a component. So now this is a blocking method that's going to wait until the phase in which this sequence is running is ready to end. And then at that point, when the sequence detects that we've reached the end of the phase, we could choose to extend the phase. You can debate whether or not that's good practice, or we could tidy up the sequence and do any housekeeping that's necessary to tidy up the sequence as we jump out of the phase. So some sequences are naturally associated with a particular phase in the generation of stimulus. So for example, you might have a sequence to do a reset or a sequence to perform the main action of a test. Other sequences are reactive. So if we want to describe some reactive stimulus, what we could do is to choose to start our reactive sequence in the reset phase, for example. Then when we'd reach the end of the reset phase, of course this sequence would get interrupted, and we'd have to do something like we saw in the previous slide in order to recover when the sequence got interrupted. Then we'd go into the next runtime phase and we'd have to detect that and restart this sequence. Well, that all sounds very clunky and error-prone, and it's probably best just not to do that. So, to cut to the chase, if you've got some reactive stimulus, if you've got a sequence that would naturally span phases, it's almost certainly better not to use the UVM runtime phases, but to start such a sequence from the run phase. The reactive sequence can then run by itself throughout all of the UVM runtime phases. Another caveat concerns phase jumping. UVM 1.2 has cleaned up a number of aspects of the runtime phasing such that they work properly. That includes the jump method. So we can now do phase jumping by calling the jump method of a domain. So domain1.jump will cause all the components in domain 1 to jump directly to the given phase, in this case to jump directly to the reset phase. So jump is like a go-to for phases. It works, but like go-to, it's intrinsically bad practice, if you like. So just like a go-to in programming, sometimes you can argue that go-to can be an appropriate thing to do, but only in very specific prescribed circumstances. So one circumstance in which you might want to jump is to jump backward to the reset phase. So if you're going to jump backward, that should really be restricted to jumping back to earlier runtime phases. You could also use jumps to jump forward, and if you're jumping forward, that should be restricted to jumping to one of the common phases that follows the run phase. So in other words, it's reasonable to use jump to jump back to the reset. It's reasonable to use jump to abort the run phase and jump on to one of the post-processing phases. But when you call domain.jump, what that's going to do is to abort the phase methods of all of the components in that domain. And as a result of doing that, it's going to clear all the objections associated with that particular phase. It's also going to kill any child sequences of the phase methods. And intrinsically in System Verilog, it's going to delete any objects created by those sequence processes. And in doing all of this, there are absolutely no safeguards, no guarantees. When you jump out of a phase, any processes or objects associated with that phase are just killed outright. And there's no built-in safeguards, no built-in checks, no built-in guarantees that you haven't broken anything. And because of that, the best advice with regard to phase jumping is simply don't do it, unless you know exactly what you're doing and why you're doing. So phase jumping works in a well-defined way in the sense that when you jump from a domain, all the components in that domain do indeed jump straight to the given phase, but it works in a rather drastic way because it just kills dead all processes and objects associated with that executing phase, and it's entirely up to you to sort out the mess. So that brings us on finally in the last few minutes to VIP integration and recommendations. So our first recommendation is to keep VIP phase agnostic where you can. So if you're creating an agent, you might want to define a bunch of sequences to perform actions on that agent, such as a reset sequence, a configure sequence, and a run sequence. And at this stage, there's no reason to introduce runtime phases. Why would you? You can just write sequences to perform the necessary actions, and that gives you complete flexibility to execute those sequences whenever you want, which could be from other sequences, from virtual sequences, or from runtime phases. Runtime phases only come in when you start building environments around those envs. So suppose you integrate your verification IP into an environment and you want to call those sequences. You've then got a choice. You could write a virtual sequence to call each of these sequences in the appropriate order, or you could make use of the runtime phases. It was a good thing to start these sequences from runtime phases where they're a natural fit. So we might start the reset sequence from the reset phase, the configure sequence from the configure phase, the run sequence from the run phase. So where it's very natural and obvious which of these phases you should be starting the sequences in, you can do so as an alternative to starting these sequences from a virtual sequence. For a number of years now, some UVM experts have argued that you should be starting sequences from virtual sequences from the runtime phases, because the runtime phases were not particularly well defined and have a number of pitfalls associated with them, most of which I've described during this webinar. Now runtime phases do work a bit better, so you've got a choice. And if you choose to start these sequences from runtime phases, then you may be in a better position when it comes to integrating higher level environments as we move up and up the hierarchy. So when it comes to integrating individual agents, you could unpick your virtual sequences and stitch them up again so things happen in the right order. When things become more complicated, there may well be advantages in using the runtime phases for this purpose, because now it's really sweet to use the sync method to actually synchronize runtime phases between different domains. So what we can now do is simply place these two M's in separate domains, domain 1 and domain 2, and then say domain2.sync domain 1 in order to synchronize specific methods across domains. But you should always beware assumptions when integrating verification IP. And this is the first principle that comes way before we start considering the nitty-gritty of the infrastructure. Always check assumptions. So whether or not runtime phases are being used, whether we're using virtual sequences, built-in runtime phases, user-defined runtime phases, whatever, always check your assumptions. And with that in mind, it can be a good idea to introduce user-defined phases wherever it's not totally obvious what the predefined phases are doing. So for example, if you've got a training sequence, where should you run that training sequence? Should you regard it as part of reset, part of configuration, maybe part of the main phase? Well, it might be clearer in this case to introduce a new user-defined phase. So our advice is use the built-in runtime phases where they're a natural fit. Where they're not, introduce user-defined phases and give them a descriptive name to make it much clearer what's going on. And we can then use the sync method in order to synchronize phases between domains. And the beauty of this is that we can synchronize the predefined phases and the user-defined phases alike. Sync is totally agnostic as to whether it's working on predefined phases or on built-in phases. But one thing that sync can't do is to order phases across domains. So suppose that you want the reset phase in one domain to occur before the reset phase in another domain. Well, we can't just use sync to do that directly, but what we can do is make use of pre and post phases. So we suggest that a really good idea is to reserve the predefined pre and post phases for synchronization across phase domains. So here we're syncing the reset phase of domain 1 with the post reset phase of domain 2. And again, we're syncing the shutdown phase of domain 1 with the pre-shutdown phase of domain 2. So making use of these pre and post phases just for synchronization across domains turns out, we think, to be a really neat thing to do. If you look in the UVM 1.2 documentation, you'll find a lot of rather ambiguous notes on the distinction between pre-reset, reset and post-reset, pre-configure, configure and post-configure. I challenge you to figure out from the documentation the difference between what you should be doing in the post-reset phase versus the pre-configure phase. It's all pretty ambiguous. So we think it's much safer to avoid actually overriding the pre and post phases, but it's really neat to use them for synchronization. So in summary, recommendations. Do write sequences for doing actions such as reset configuration. You can then choose to start those sequences from the predefined reset configure main shutdown phases where it's natural to do so. But only use these runtime phases for stimulus, for nothing else. Add user-defined phases where the predefined phases are insufficient. Use domains and then use the sync method to sync phases across domains when integrating verification IP, but restrict the pre and post phases for synchronization rather than overriding them, because that leaves too much to chance. And then finally, you can use phase jumping, but do not use phase jumping casually. There's absolutely no safeguards and guarantees built into phase jumping, so only use it if you're sure of what you're doing. So that brings us to the end of this webinar. All the source code associated with the webinar, you can download it from this URL. So go to doulos.com, downloads DVCon 15. Incidentally, this information was first presented as a paper at DVCon 2015, and you can actually download the paper from this URL, as well as a full set of source code examples. If you want to know any more about training from Doulos, that includes training on UVM, as well as system Verilog, hardware design, embedded systems, FPGAs and ARM processor technology, then you can visit our website, www.doulos.com, and check out the details. So, thanks very much for your attention. That's all for now, and I look forward to seeing you on a future webinar.